So you had some interesting dates there for future activities. Are you going to talk about that later? Yeah. Okay, very good. So today, I want to say that it's going to be a day that goes up and down, in and out of technical and practical aspects of what's new in version 7. And we're going to start off in perhaps the hardest part of today. There are going to be 2 topics that we're going to cover in about 50 minutes. And they're going to be led by, or introduced to you by Tihomir. It's deliberately chosen to be happening during this morning when you are rested and can handle advanced things. Some of you are going to think, boy, this is far out. Or to use the language of UCLA students, oh my God, this is like weird. And it is, but it has opportunities for new types of research designs, new types of data collection designs. And I really think you should try to penetrate it. Then it gets easier. Perhaps one of the most popular or most easily accessible parts of the 2.5 days together is what comes next in the last 30 minutes before your coffee break this morning. And that has to do with mixture modeling. So nothing to do with multi-level at all, but back to the basic mixture part, the mixture heritage of Mplus. After that, we have the afternoon, which goes into multi-level modeling, 3-level and cross-classified data. And I think you will find that relatively easy compared to this morning, the start, and relatively easy compared to yesterday. So we will be talking about things like regression analysis, path analysis, down-to-earth things with a simple extension beyond the standard 2-level. Tomorrow morning is going to get hard again. Tomorrow morning is a futuristic morning, but again, it has great potential for future research, be it both substantive and or methodological. So with that, I'm not going to steal any more time from Tihomir, but hand over to him.
Thank you. So, I was just going to say about this stuff with the language. So that's one of the reasons actually we got delayed with version 7 is because Linda basically didn't like the language, and that was good. It would have been much worse to try to explain this model with the language we had before. So we're kind of actually proud of the, the simplifications we made in the last the last month, but I guess we got delayed with the release. So we're going to talk about a little bit more about random loadings, and I'll just give you a little bit of the history, actually, how we actually ended up with being excited about this modeling. So the first, I think, encounter we had was when we released ESEM back in 2010, and Herb Marsh actually came in with this big data set and started, which was the data set that had feature evaluations. It's an old data set, and he had basically 60 groups, and he was trying to do these EFA models on these 60 groups, and there were all kinds of misfits, and he went wild in terms of how to modify the models and which loadings, which groups, the groups non-invariance, and there was the model looked so scary at the end that we thought that, we really need to find a better way of doing this stuff so that people don't really need to go through a billion modifications for the loadings to actually get the fit to work. So that was our first encounter, first thought about this. Then in 2011, I guess, we went to this conference and we were doing some other stuff, and we were talking about these algorithms, and during the breaks, I talked with Bengt, and we realized, this algorithm actually would work for random loadings. So, and then we put a little slide, just a surprise slide there, and people got really excited about it. So we thought that eventually we need to really be serious about this stuff and really do it. And then we did some stuff, and I went to this conference in Vancouver, and I met Jean-Paul Fox there, and he pioneered a lot of this stuff together with Martin de Jong. They had an article in Psychometrics. Anyway, I was trying to talk about random loadings in Vancouver, and we realized the models that they were talking about are not quite the same as ours. So they have this random item modeling that's somewhat different. So, but we actually went back and did some more modeling. So right now, random loadings are basically implemented in two-level analysis and also in cross-classified analysis, which we're going to talk about tomorrow. But when we were doing, so when I met Jean-Paul Fox there, and he kept on referring to his book. And, I was so surprised that he has a book on this stuff. And I ended up getting a copy of the book and went back home, and I realized I already had a copy. So it just kind of, we missed how much actually work was already done in this area. So that's basically, this book here actually has a ton of examples with random loadings and all kinds of random parameters, and it has a lot of substantive examples. He doesn't use Mplus. Mplus didn't do these models until now. So, but if I can convince you today that this is an exciting new opportunity, new modeling stuff, you have to read that book and get convinced for yourself. And again, he has many substantive examples there. And I'm actually going to use one of his examples to illustrate some of the issues that we have now. One of the things is, yesterday I talked about when you estimate Bayes EFA, that the models are not quite identified, and you have to keep track of the signs of the loadings, and these actually, we haven't actually implemented constraints that restrict the sign of the loadings when the loadings are random. And the reason we haven't done that because we haven't encountered any examples where that actually happens. So, but we can do it, but we first need to see an example where that really happens. So maybe you guys can help us, run your own models and watch out for sign flips of the random loadings. And if you see that it happens, then just let us know, and we'll work on that. So, so anyway, I'm going to go to my first example here, which is an example of two-level random loading IRT model. And this uses the PISA data. So finally, we have an interpretation of what PISA stands for. It's a Program for International Student Assessment. And this is basically a large sample. We have nearly 10,000 students from 40 countries across the world. And basically, this sample extracts 8 binary items that are going to measure math ability for the students. And this example is in Fox's book, and also it's in this paper, cross-cultural analysis. That's part of this book, cross-cultural analysis, methods and application book. So we have 8 binary items, and we're going to basically construct a one-factor analysis model with these categorical indicators. So a simple IRT model. The probability of correct answer. So Yij is outcome for student I in country J and item K. So the probability of answering correctly is the standard two-parameter IRT model, except now we're going to allow a lot of country-specific parameterizations. So the first thing is that the discrimination parameter AJK is country-specific. So that's basically a normal random effect that has a mean and a variance. And the difficulty parameter is also country-specific. It's a normal random effect. And of course, from structural equation point of view, this is just the concept of a random loading and a random intercept. On top of that, we want to allow the math ability parameter theta ij to have a country-specific mean. So that's every country. So that will allow us to evaluate the math abilities across countries, and then we have a residual for the math ability. The residual in general, in principle, the residual here should have a variance fixed to 1, but we're going to also allow the variance for the math ability to be different across countries. So not just in principle, we're interested not just in the mean to be, the factor mean to be different across country, but also the variance, right? It makes sense. You have, if you have an observed variable, say, income, right? The average would represent basically the wealth of the country, but the variance would represent the disparity within the country. So both of these quantities are quite meaningful. And the same thing with the math ability. Again, we have this, the variance here for the math ability is different across country. In principle, that's supposed to be fixed to 1 to identify the scale here. So we actually, instead of fixing this to 1, we want it to vary across country. So this is a positive quantity, so we take the square root of that, and we can model this as a normal random effect. And to identify the scale, we have to fix the mean of this square root of the variance to 1, and that's going to identify the scale in the IRT model. Now, an important feature here is the fact that we can interpret, even though the loadings, the difficulty in the discrimination parameters are different across country, we still want to have the same interpretation as we have it with regular IRT, namely that you can compare that the quantities are measured on the same scale, right? In order for you to compare, a math ability across countries, you want to have this interpretation of this model that this is the same, that this is on the same scale. And we argue here that because these difficulty parameters, the discrimination parameters, are going to have small variance, and therefore we interpret that country-specific loading parameter as a minor adjustment of the model, really, so that we can interpret this as being on the same scale. So that's going to be an important thing in this modeling, that if the random loadings actually have too big of a variance, then we have to question the meaning of the model. But as long as the random loadings have small variance, then we can interpret the model as being on the same scale and the factors being on the same scale. So we're going to talk about several different models. I'm going to illustrate several different models. We're going to talk about three two-level factor models just with random loadings. And then we are going to discuss testing of significance of the random loadings, right? That's a very essential component in this modeling here, because we're introducing a lot of additional random effects, and we want to have a way to tell whether these are significant or not, whether they're really needed. So that's a critical part of this modeling. the testing of the significance of the random loadings. Basically, if you have what we need to test is basically that this variance here is non-zero. If it's non-zero, then this loading is really random. If it's zero, then it should be just a standard loading, and we shouldn't have a random effect there. So it's very important for us to understand and be able to evaluate the significance of this random effect. And of course, if the variance is zero, then you have basically a loading invariance. The loading will be the same across the countries, and so you can have the same. What that means is basically that one of the items, if you have a random loading that's fixed that has a zero variance, that means that the item is measurement. It has measurement invariance, and it's basically measuring the matability the same way across countries. So cross-country independence. So we're going to talk about the testing of significance of the random loadings. Then we're going to talk about, so the first three models are not going to have the factor-specific variance. So for the first three models, we're not going to have this portion of the model where the factor variance is specific across varies across countries. So it's going to be fixed to 1. And then we're going to have two different ways of actually adding cluster-specific variance. And all the models that I'm going to talk about, they're presented here within the IRT framework, but you can actually use them with continuous outcomes. So before I move on to the next slide, I wanted to say that just have a second to think about what multi-levels model do. In general, we have random intercepts. That's the very basic of Mplus. You put a y variable on the within level, you put it on the between level, and what that means is that the across cluster, the mean across clusters for that variable is changing, right? So we have a cluster-specific mean. As long as you have a variable in a two-level model in Mplus, and you don't declare it as a within variable, you basically have a cluster-specific mean for that variable, right? But what about the variance? Does the variance change across clusters? If you have 100 individuals across within each cluster, and you look at just the sample statistics, right? You can just average within that cluster, get a cluster-specific mean, right? And you can see how that would change across the clusters. You have, say, 100 individuals within each cluster, and this quantity is the sample mean and the sample variance would be fairly well estimated. If you have a large enough cluster, both of these sample statistics within the cluster, they will be fairly well estimated. And so everybody knows that, in a two-level model, the mean should vary across clusters, right? Well, what about the variance? Why haven't we talked about the variance before? Do we really believe that the variance is the same across clusters? And, again, if you have large enough clusters, I can almost guarantee you that those variances are not going to be the same. So that is this same thing here, except it's for the factor model. But you could also do it for observed variables. So how do we actually start having these elements in Mplus where we can also explore the variance being different across clusters? It's a concept of heteroscedasticity, of course. But what we're going to present, in Mplus version 7 is basically a much easier way to deal with that and actually model it and get, statistical significance and things like that. All right, so here's the first model. And basically, it's the same model as the one I presented before. We have only one simplification, again, that the variance of the factor. So this is basically the factor mean, the country-specific mean for the matability. And the variance of that matability is 1, basically. So it doesn't vary across country. So that's the main, this is basically the first model. We're going to focus on this first model for a little while. So we have no cluster-specific factor variance. And this model is just so much easier to, it's such a fairly easy to actually work with, so we're just going to introduce this model first. But, so we basically drop one of the features there. But let me just say one thing. If you actually drop the factor, cluster-specific factor variance, can I convince you that that's not going to lead to a model misfit? If you have cluster-specific factor variance, in principle, the scale is not identified, right? So the loadings and the square root of the variance of the factor, they confound. You can fix the factor variance to 1, and if you want, so not have any variance in the factor, and just take that and take square root of the variance, put it in the loading, right? So in principle, variation across country in the factor loadings is confound with the variation across country of the factor variance. So I have to say this like another 10 times because it's a key concept. We have to just get through this concept. So let me say it again. So variation across country in the factor loadings is confound with variation in the factor variance across country. So these two concepts are intertwined, and we need to have actually a way of separating the two. We need a model that can easily separate the two in a meaningful way. Right, we just talked about it. This is an important thing, right? It's not some artificial concept that kind of comes up out of math. Because you want to evaluate, so why the loadings change? Because they change because in different countries, these instruments are not measuring the same thing equally well, right? So the different items actually have different qualities in different countries. And that's why the loadings change across countries. And then why do the factor variances change across countries? Well, they change across countries because there's more disparity in some countries than others. So we need to, these are two substantively different concepts that we actually need a good model to evaluate the difference. And so we're going to present this, what we think is these really good models that we've come up with, and that actually will separate really well these two separate variations across country. But no, first of all, what I wanted to say is actually that in terms of fit, just ignore the interpretation for a second. In terms of fit, you cannot actually get a misfitting model because you fix the variance to 1. Because if the variance was actually different across countries, you essentially push that variation out into the loadings. So you cannot get a misfit. So this is a good model even though it doesn't have the country-specific variance. So how do you specify a model like that? You've already seen the language yesterday. It's just a simple statement like that. It's the standard F by measurement here, except you have random slopes now. And those random slopes, the means of these random slopes are going to essentially have we'll have the interpretation of the standard loadings, the usual loadings, and except that those random effects are going to have means that are the usual loadings, but they also have some kind of a white noise implemented. And so on the between level, you have these a lot of latent variables here, random effects. So this one is basically going to be the country-specific mean of the mathability, right? And then these are basically going to be the country-specific difficulties, and these are going to be the country-specific discriminations. So we've got 17 random effects right away. In the simplest model we can think of, already has 17 random effects. And of course, this takes, in terms of estimation, straightforward. It takes a minute to do it. And so, and this is really the breakthrough here, because again, you could do this in ML, but with some kind of a numerical integration that's going to be super hard to do. You need incredible computer and incredible patience and ability to actually monitor the computation and things like that. Not here. You just specify a simple model like that, you run it, you get your estimates. So it's really straightforward, despite the fact that it has so many parameters, so many random effects. And so, actually, I have to say this. So we're presenting two different methods of actually dealing with country-specific parameters here, right? So one of the options is the diff option that Bengt talked about yesterday. And this is a different way of doing that. So the two separate methods that we are describing, and remember how many parameters some of Bengt's models had yesterday? 2,000 and plus, right? How many parameters do you think this has? 24, right? Or something like that. 4 times 8, essentially. So this actually, it takes all these parameters and puts it in the random effects, and so it becomes a little bit more parsimonious. But we also talked about the fact that those parameters with the diff options, they're not really regular parameters because they're so confound to each other. So again, it has the same flavor, that they're not quite regular parameters, they're parameters with a little bit of noise. And here are the estimates of this example, and these estimates are pretty much the same as the one reported in Fox's book. So these are basically the means of S. Again, these are the standard loadings. These are the average loadings values across countries. These are the threshold parameters, the average difficulty parameters across countries. And you scroll down to more output, and you get the variances for all these random effects. And you can see all these estimates. They're not very large. Here's the estimate for the between variation for the factor, and you can, the variance on the within level is fixed to 1, so you can compute this way the interclass correlation for the matability, and that's about 30% or so. And also here the variations in the random loadings. Now you can see all of these are quite small, right? And so right away you start asking the question, are these really significant? Do we really need these random loadings there? Can we just use the fixed loadings? And that leads to, okay, so yeah, you can actually do a lot more stuff here. You can actually get, using factor score, the factor score stuff in Mplus, you can actually get the country, for each country you can get discrimination parameters, difficulty parameters, estimates. You can compute, these are the country-specific factor mean, and this table actually has the country-specific matability mean that came out of this model. These are basically the top three countries and the bottom 3 countries here, and you get confidence intervals. So Finland came out on top. I think everybody knows that, right? But we needed tomorrow to show it again. So, and you can also get some plots like that for the country-specific matability. Basically, you can get an entire distribution. This looks fairly normal. These plots are part of Mplus now. And this actually is new, right, in version 6. I think you probably, I don't know if you've ever tried to actually plot the distribution of a factor from Mplus, but yeah, we didn't have that before. This just comes out now in version 7. So I'm just going to put the table again here so we can look at these parameters. So you can see the loadings are very small, right? So this loading here, S8, has a variance of 0.01. So what exactly does that actually tell us is how much is the variation in that loading across countries? Well, you have to compute the standard deviation. So the standard deviation for this will be 0.1, and then the standard loading varies from plus minus 2 times the standard deviation, right? So you have a total of 4 standard deviation units is the range of that loading, which in this example is 0.4, right? So that actually is a small variance, but what is the loading for the mean for S8 is 0.6. So a range of 0.4 is actually fairly substantial, right? If the loading is 0.6, that means that this varies from 0.4 to 0.8. So even though you get these small variances for the random loadings, actually it actually has a substantial range. The estimates are going to vary quite substantially across countries, so you should actually be interested in these random loadings, even though the variances come out small. And the question comes right away, is this actually statistically significant? Is this random, is the variance parameter of the random loading statistically significant? And you know that this is a difficult problem, right? If you follow the statistical literature, there have been so many articles, and there's still active research about how to do that. There's no dominant methodology yet. But we can give you a few simple recipes about how to actually perform this easily and how to perform it rigorously in some cases when you need to. So the problem you have that in maximum likelihood you cannot do likelihood ratio test for a significant variance component, because that test is a test for a border parameter. So testing for the variance to be equal to 0, the variance is always positive. You're testing against a borderline parameter, and in that case the likelihood ratio test is not the usual chi-square, and so it doesn't work. There's some simple recipes in certain situations, but those simple recipes break down, and in a lot of cases you actually don't know what the actual distribution of the likelihood ratio test is for testing that significance component. So the same thing with the t-test. It's not a reliable method when the variance is near 0. However, if the variance is not near 0, then we're not at the border. And so the confidence interval is actually reliable. And here's a little example. So the variance of S2 is estimated at 0.78 with confidence interval this. And this is a base confidence interval, but remember that base and ML are the same thing really. Just base, we're using base as a computational tool here. So you can think of this as being actually the standard t-test essentially. And asymptotically they'll be the same. The bottom line is that this interval here doesn't include 0 at all. It's not very close to 0. It has enough room there, so you can say that as long as that interval is away from 0, we can actually trust that interval, because we're not at the border. There's no breakdown of the theory, and that's why this confidence interval is okay, and we can conclude that this is actually statistically significant. Now, here's another example. The variance of S7 is this value, 0.006, with confidence interval like that. Well, at this point, you have to start questioning. This is already too close to 0. That, one of the things is that confidence interval, when in the base estimation, the confidence interval cannot include 0, right? Because the confidence interval is based on a posterior distribution. And so these values are always positive. So that confidence interval is never going to go from minus 0.01, and you can say that this is not statistically significant, right? Do you guys understand what I'm saying here? You've tried to do that, I'll show you what I'm saying. Actually, here, look at this stuff here. Let's try and do the usual thing. Try and determine the statistical significance of these things based on the confidence intervals. Well, this thing never goes negative. And that can never go negative, because it's just the posterior distribution of all these variance components within the base estimation. They will always be positive. So that's not a way to do it. It is a way to do it right here, because it's okay. This is a confidence interval, and it's away from 0, so it's reliable. And I'm saying that even for this one it's okay, but it's not okay here. So in these cases, when the variance is too close to 0, what can we do? And basically, we learned this new method actually from Fox has a paper on this stuff, and it's now implemented already. So the paper is brand new, and we already implemented this in Mplus. We were so excited about this, and used it a few times, sufficiently to test that this actually works fairly well. And it's based on a base factor. And in this case, when you test the hypothesis of sigma equals 0, that hypothesis is basically replaced by hypothesis of sigma less than 0.001. And to actually test this, you have to insert a prior like that, inverse gamma, very specific prior. This is not something you can choose on your own. You have to use that prior to test the variance. And so what that prior does is basically it tries to push the variance towards 0, and if there is enough, and see, when you push the variance towards 0, you basically want to see whether the data will provide resistance to that variance being pushed to 0. And you basically evaluate this base factor, and the base factor is the ratio of these tail probabilities, and as long as the posterior distribution has less tail towards 0 than the prior, you can conclude that the variance is statistically significant. So the base factor, if the base factor is greater than 3, then you conclude that there is statistical significance. And this is implemented now in Tech 16 in Mplus. And I'll show you, here's an example, here's that example. So you have, and also, so the two things. So the way you actually run this new test from John Paul Fox and Verhagen, you can estimate your model the regular way, not putting any prior, just using an informative prior. And if you want to test a specific variance, you have to run a second run. And this is what the second run looks like. It's the standard model, except now you add these priors. They're very specific priors. Again, I would not recommend changing this, because all our simulations show that this is important to actually put exactly that prior. And you basically get in Tech 16 this table, and this prior actually corresponds to this table. We have different threshold levels for which hypothesis you can check, but basically you have to look in the second column. And as long as you get a value that's greater than 3, you can conclude that this parameter 28 there is not statistically significant random effect. It should be fixed to 0. So you can actually fix that parameter to 0. Let's see. So yeah, this is basically, this parameter here is the third random loading. And you can, if you want, you can actually run it as a fixed effect. So you can just, it's the same statement. The first two loadings are random. The third one is a regular loading, and then loadings from 4 to 8 are random again. Now, even though this is almost like it looks like a very simple input, actually this an entire different algorithm goes in here, which of course even I can't tell you what it is, but it's required a totally different algorithm to actually do this estimation. But the bottom line is you can actually have a mixture of fixed and random loadings in the same model. One of the other things that I was going to mention here, which is described on this slide, is that we've done we did enough simulations now to test where this method actually works for testing the variance components. And after enough simulations, we realized that if you're going to do this kind of testing using the new Tech 16, you have to have enough iterations, enough MCMC iterations, because as I showed you on that other slide, the actual base factor is basically a ratio between two tail probabilities. And to estimate the tail probabilities, you actually need a lot of iterations. And so this command that we just introduced again in version 7 is we elaborated now on the bitter command, and you have 100,000, this is the maximum number of MCMC iterations that you can take. That used to be in version 6. And now in brackets, we put the minimum number of iterations that you can take, that the program should take before stopping, and it stayed 10,000. And basically, if you read through this slide, you realize that unless you have that minimum of 10,000 iterations, the TeX16 results might not be reliable. And so I'm going to continue to the next model. In this model, what we changed now is that, Bengt talked about this before, is in IRT modeling, the loadings on the within and between are the same. But in Mplus, it's a general program. We don't have to have that restriction. So you can actually have the country-specific mean have different loadings, not necessarily the same loadings as the within level factor. In that case, you have to fix the variance here of theta j to 1. Another model is where, and of course, this is again, it's easy. This model can be easily specified in Mplus. Here's another model. Let me actually just put the input for that one. So in the previous model, actually, one problem when you end up with different loadings for the within and the between, you cannot quite interpret theta j here as the factor-specific mean, right? Because it's measured somewhat differently, so the interpretation is a little more awkward. So what, as an alternative, what we thought of is that you can actually have those loadings here be the mean of the random loadings. So the loadings on the between level can be said to be the means for the random loadings on the within level. And here's how you do it. And this way you can sort of preserve the interpretation of the between level factor being the average across country mathability. And here's basically the setup for this model. It's pretty simple. Again, it's the random loadings setup. And here the means of the random loadings, and you add these parameter labels P1 through P8. And FB here is going to be this parameter theta j, and it's going to be the factor mean within each cluster. And those loadings that measure this factor mean are going to be the same as the means of the random loadings. And this way you kind of have the same scale, except that on the within level you allow these additional adjustments within each country. Okay, now I'm running out of time very quickly, so I think method 1 is going to be, this is basically, I'm going to go through two methods basically that allow to specify the country-specific factor variance, for the factor, and if you, this is basically, I'll just very quickly go over this, but essentially this is our factor here, and we take off the residual of the factor, which is going to be E, and put it again as a random loading. So this is a random loading of the, so it's kind of a double random loading here. So it's essentially there's a factor behind the factor, and that also has a random loadings. And if you just look through these formulas, you can see that the variance of theta j changes across factor. I'm just going to go to the other method because I think it's more important. Okay, so this just a little bit of a just a little bit of math so I can actually convince you that this is a great idea. So I'm about to tell you a really great idea, so I hope you can get it. This is quite an amazing thing. It's the bullet right here. So the between level, so the variance is actually a factor between behind the random loadings. So, but anyway, so so the variance of theta j, we want to have this be country specific, and we want this to be 1 plus sigma j, where sigma j is a random effect. And as I said before, you can actually push that change in the variance of the factor into the random loading, into a difficulty parameter here. And so the difficulty parameter can be set to be this value, right? It changes. That's the original value of the random loading, and now it absorbs the factor variance. And so that's the new random loading. And if you actually expand this thing, and sigma, both of these terms are kind of residuals that are small, and the product will be even a smaller magnitude. It's kind of a standard thing to do in math that, you know, when things are very too small, they just drop out. And so what you get is that the random loadings is a fixed, the fixed loading plus a residual, plus the same loading multiplying this random effect sigma j, which is the change in the variance. And what does that tell us is that this is actually a factor model on the between level. That's the mean, that's the loading, and that's the factor. And so to actually do this model you basically, oh, that's not the right model, sorry. There, this is the right model. So look at this, it's a little crazy stuff here. We have 3 sets of parameters on the between level that are fixed to be equal across each other. But again, what this thing says here that if the factor, the cluster-specific factor variance is the common change in the random loadings. So in order to introduce a country-specific factor variance, all you need to do is actually have a factor behind the random loadings. So that's, I think that's, I'm not sure how to emphasize that, but this is kind of a, so basically, this is the factor-specific variance, sigma, and what is actually, how is it introduced in the model? It's a factor behind the random loadings, right? And, you know, this is basically the factor model, and you see that the mean here and the loadings in this factor model are the same. So you've got these constraints here, and FB is again the country-specific mean. Any questions with this stuff?
I don't think you should take questions right now.
Okay. Yeah, it's a kind of a great model. I think it's, it's kind of hard to explain in a short period of time. So we have a paper that actually discusses this in more detail. And I'm going to go through a next example, basically, which is, yeah. Yeah. How are we doing with the time?
Do you mind if we save this section and have it in a special at the end of lunch?
Yeah, sure. Yeah, I think, okay.
It doesn't connect totally with what the previous, right?
Yeah, we can do it later. So do you want to, I think, do you want to step in and introduce the next topic then? Yeah, okay. Okay. We'll save the other example, I think, for a little later. Sorry.
So am I audible back there? Okay. So I want this topic that's coming up now to be emphasized a little bit more because I think it's a breakthrough. And I suggest that we take it as use part of the end of the lunch. Come here a little earlier and go through this. So it gives enough emphasis on it instead of rushing it through right now. And we could be back here at maybe, well, we can discuss that when we get closer to lunchtime. So I want to go into something to relax you a little bit and go to slide 37 instead. So now we're taking a short break from multi-level modeling, which has an enormous amount of new possibilities, as you might surmise from Tihomir's presentation. And he pointed to this high-dimensional paper, that and the other paper that we mentioned, which we call the NCME paper because it was presented there first in Vancouver in March by Tihomir. Those two papers are papers that are not yet posted, and they will be posted shortly. We just want to polish them a little bit more. And then part of them are going to be submitted to journals, but part of them probably won't be, because there's so many things that we've explored that it won't fit into an article. Perhaps if somebody edits a book, it could be a good book chapter. So let's instead now switch over to mixture modeling and introduce some new features. And I want you to focus on this picture. It's single level analysis, and I want you to ponder the situation where we have a set of indicators of a latent class variable C. In this case, we use a generic Mplus notation of U, which is for non-continuous outcomes. So imagine that these are binary indicators. But know that latent class analysis, as this is called also, latent class analysis can handle any kind of indicator, be it categorical, binary or ordered, ordinal, continuous, count, or even unobserved. So these could be unobserved variables that are measured higher up here in the ceiling. So we have all kinds of possibilities to study underlying latent classes. So we call these the latent class indicators, and we often have an interest in explaining the tendency to be in a certain latent class as a function of covariates X. So here we have two covariates, and they influence the probability of being in a certain class, which in turn influences the probability of answering yes or no to these items. In addition, we're going to talk about a so-called distal outcome, which is a consequence of the latent class variable. And typically in Mplus, we do not say Y on C, but instead we pay attention to how the mean or variance or thresholds vary for Y across the classes of C. The question then comes up quite often, if you want to do an analysis of this latent class variable, how should you go about using the three sources of information? The indicators, the covariates, and the distal. And one way of doing it is by the standard single-step approach of, say, maximum likelihood, is to use all those pieces of information in one single step. The one-step approach, because all of these variables, not only the indicators, but also the covariates and the distal, have information on C, on the class membership, because they are correlated with class membership. Therefore, they carry information about the latent classes. However, many substantive researchers don't feel comfortable with introducing or adding the information of X and Y to the determination of the latent classes. They only want to use the U variables. In fact, our Dutch colleague, Jerome Vermunt at University of Tilburg, a very sharp gentleman who has a mixture program. I momentarily forget the name of it. All right. He quoted, if you read this, you can read this on your own. Take a minute to read this. It's a reading assignment, and you'll have questions on it. So how many of you agree with this critique of the one step? Don't be shy. How many of you disagree with it? I think you're ready for three-step. There was a lot of agreement and no disagreement. Now, so here's a particular example, and it really boils down to a substantive question. Should the latent classes be defined by the indicators alone or also by the covariates and distals? So one typical example that I've encountered users of Mplus bringing up is the study of genetics. You have this genetic information, and these genotypes are observed variables that influence phenotypes. In this case, it's the U indicators. And the U indicators could, for instance, be DSM, Diagnostic Statistical Manual for Mental Health, criteria. In this case, it would be 5 criteria. And the interest would be in finding latent classes, as it says, of subjects. And then trying to see if a certain genotype influences class memberships. You're focusing on genotypes X here influencing C. And the possible objection to the one step is that if the genotypes are part of deciding the latent classes, the assessment of the strength of a relationship is compromised or confounded, one could argue. You don't want to create the classes so with the information from the genotypes. You want to create the classes from how the person behaves. They're behaviorally defined latent classes. And then, in a separate analysis, you want to see how the classes relate to the covariates. So that is the three-step idea. Determine latent classes based only on the phenotype information. That's step one. Then classify the subjects into the latent classes that they most likely belong to. That's step two. Then relate the classification to the genotypes. So the last step then is, after having made C observed, so to speak, by the classification in the second step, we have obtained an observed nominal variable. And we want to regress that observed nominal variable on the two covariates. That's the standard multinomial logistic regression, which can be carried out in Mplus and many other programs. The question is, though, how one does this three-stepping. Yes?
In step 2, you classify the subject, right?
Yes.
And do you use the final class? Do you use class as an observed variable then? So you get rid of the probability of belonging to class 1 or probability of belonging to class 2, etc.
Right.
So you lose that information.
We will see exactly how we do it, but essentially you want to classify subject in some way and then use that as an observed variable in the third step. But we're going to see different approaches lose different amount of information. It's a wrong way of doing it, and it's a right way of doing it, to put it simply. Now, before we get into the three-step, I want to just tell you that I think there are certain advantages of the one-step over the three-step. We will find, Tihomir will show us soon, that in cases of low entropy, that is, poor classification quality, and in cases of small sample sizes, it is probably the case that the one-step performs better than the three-step. But there are many cases where the three-step will become useful if you do it correctly. One issue, however, is the case of direct effects from covariates relating class indicators. I'll just take 1 minute to explain that. Say that this broken arrow is actually a significant arrow from one of the covariates, say, to one of the indicators. So say that you actually generate data, which you can do in Mplus. You could do this exercise. You generate data where X influences C and C influence the U's, but you also let one of or some of the covariates influence some of the indicators directly. Now, if you want to analyze only this part, only the U and C part, then you will find that the regression of U1 on C is misspecified, because C is not the only predictor of U1. U1 is also predicted by X1. But if you don't have X1 in the model, you will have an omitted variable bias. You have left out one of the predictors of U1, and when you do that in standard regression, this slope, U1 on C, is going to be misestimated. And if that slope is misestimated, the classification of people into C classes is going to be incorrect. So the class percentages are going to be incorrect in principle. So you can see where the error lies. I go through that actually in the 2004 book chapter in Kaplan's handbook on longitudinal modeling. And it's on our website, 2004. I go through that in a growth mixture modeling context and discuss these issues. You would not have a problem. Say that you don't have this broken arrow, but X's influence C only this way, only influences the U via C, I want to say. So you don't have any direct effects. In that case, statistically speaking, you are committing no mistake, no error, by analyzing only this part, because the X's influence C and only the U's indirectly through C. Okay? So in that case, it's actually perfectly all right. So the issues of one-step versus three-step are pretty deep, despite the fact that we have this bias if we leave out the direct effect, and there are many direct effects. Direct effects, by the way, it's like in mimic modeling in SEM. When you have direct effects, you have measurement and non-invariance. That is an answer to the U1 question. The probability of that is not only a function of the factor, but it depends on, say, a group dummy variable. So direct effect is a measurement bias, measurement non-invariance, which is a topic of these 2.5 days. Nevertheless, you can argue still that you may want to analyze only this part as we do in the three-step because it reflects the substantive question, and it is therefore a better approach. Now, there's lots that can be said about this. I just don't want to take more time, but hand it over to my colleague, Tihomir.
Yeah, sorry about this. Okay. And so I'm actually going to go into my favorite example with the problem in this picture. And here it is. Let's go, just ignore these three variables here. And you have the LCA, right? And you measure this latent class variable C, right? And you say you have a distal outcome like that, and you want to have this regression. And you know, why not put the whole model, right? All these variables together. Well, there is a problem here, and it's a very simple problem. What happens if this y variable has a bimodal distribution? Well, what's going to happen is the c variable is going to try to fit the bimodal distribution, right? And what happened to a c variable? It's not the same variable. It was supposed to be measured by these things here, but when you put the y in here, this is going to try to fit the distribution of y, right? And so the meaning of c changes dramatically, and you might not even be able to notice that. If you just not, pay attention, what's going to happen with the one-step procedure is you're going to destroy the whole analysis because you put the whole thing in here, and the C essentially, what in principle should have happened is when you add the y variable here, you have to add a separate class, a different latent class variable that will take care of the bimodality of y, right? That would have been, but that changes the analysis completely, right? And the other thing I was going to argue again is what happens is, you can, if in this case, when you have the C on X predictors, you can add all these direct effects, but if there is a direct effect from here to U, and if you add these in the model, what you end up doing is actually taking away from this correlation between X and C, right? And so you actually, if you're interested in how good of a predictor X is on C, by adding these direct effects that will let you fit the data well, you actually essentially changing the interpretation of the latent class variable, and you're changing even the correlation between the C and X. So again, it's what we're focusing here on is substantive applications where you want to have a pure measurement model for the latent class variable C, and you want to correlate one way or the other this latent class variable with other variables. And I hope with these two examples that we discussed with Bengt, with what can happen, what can go wrong there, you are convinced that we need a different approach than just sticking all the variables into one big likelihood. So we basically want to estimate the C on X relationship, say here, the C on X relationship independently of the measurement model. And prior to version 7, we had a method actually, we had some methodology that was already there, but it wasn't working very well. And basically, we were looking for a new method. In fact, we did a lot of simulations, and we've tried many, many things, but we didn't find one. And but Vermont found one, and anyway, we implemented. In fact, in his paper, he explains how to do this in Mplus. So he actually gave us the whole recipe very ready to go, basically. So. And here's how the three-step procedure actually works. So you estimate the latent class. So this is all done behind the scenes. You generally don't need to understand that, but just a summary of what the algorithm does. So you estimate the latent class model separately. You create a nominal variable, which is the most likely class variable, which we denote here by n, from this latent class analysis. So for each observation, you basically get the most likely class. Estimated from the LCA model. And then in step 3, you use a mixture model that has this most likely latent class variable n as a indicator for the class variable, and then you also have the relationship of that class variable with another variable, so C on X, say. So n, essentially the observed variable, is said to be a measurement for the latent class variable, but what you do here is basically you insert the measurement error into this third step. You actually set n is almost exactly the same as C, except it has a little bit of measurement error. So that's the third step, basically, in the three-step procedure that we've implemented now in version 7. The methodologies, all of these things are described in this Mplus Web Note 15, and the original contribution was by Vermont, and I think it was an earlier paper that by, do you remember the name of the? Anyway, we have that information in the Web Note 15, but there was an even earlier article that actually had the same idea as Vermont. Okay. Okay, so just a quick summary of what we have implemented now in what you have in Mplus version 7. So there's 5 different auxiliary variables, and these are basically a way to estimate the latent class variable, the latent class model independently of any other relationships you want to estimate with the latent class and other variables. So if you want to estimate a relationship between a latent class variable and another variable that you don't want this to influence the latent class model, you just have to specify it as an auxiliary variable. And basically the 5 types of auxiliary variable and the type is specified in these brackets. Different types are specified in the brackets, and by changing what's in the bracket here, you get a different estimation method, as well as you get a different model that's estimated. So if you specify a variable as auxiliary with R, you basically estimate a C on X regression post estimating the latent class model, right? The latent class model is estimated first, and then in a separate step, you estimate C on X regression using the pseudo-class methodology that was implemented prior to version 7. And we kept this method for only one reason. We've never seen these old methods to be, they're always worse than the new methods. We just kept them in the program so that for comparison, basically, so people can see the advantages of these new methods. So if you want to estimate the C on X regression separately of the LCI model, you specify it that way. If you want to estimate C on Y on C, this kind of a model, you have to specify it as auxiliary with bracket E. And if you specify R 3-step, this is the same as that one, except it's with the new methodology. And distal, this basically stands for distal unequal variances with the 3-step procedure. So again, this refers to this model, the C on Y, Y on C. And there are two versions here. You know, when you estimate a normal distribution, a variable that's affected by latent class variable, you can have, typically what you have is the means of the Y variable changes across class, right? That's essentially a Y on C regression, right? But you have two separate models that you can consider. The latent class can also affect the variances of Y. So you can have different variances of Y in each class. Or you can have them be equal, right? So in this case, in this option, C actually affects both the mean and the variance. And in this case, it only affects the mean. So these are two different options. But in principle, we've done some simulations on the .web Node 15. And I think this is basically what you always want to go with. Unless you have some specific reason when you don't want the variances to change across class. And here's some simulations actually to convince you how much better the new methods are basically. So this is a distal outcome Y that's estimated. We estimate Y on C post the latent class analysis here. We have a comparison between the pseudo-class methodology, the 3-step methodology, and the 1-step method. And because there's no specification here, the 1-step method is going to perform very well. It's going to be, we can use it as a tool to evaluate the efficiency of the 3-step procedure. When you don't have any specifications, the 1-step procedure is always going to perform the best. So it's going to be the most efficient because it's a 1-step maximum likelihood. So by default, you cannot beat that. But what we want to know is how much efficiency is lost by implementing this 3-step procedure. So that's why we're comparing this with that. Anyway, you can see here, this is the first column is the bias. And you can see how much, in all cases, you get a lot of bias. The entropy is something that's kind of important here in evaluating the quality of the estimator. And you change the entropy by changing the thresholds here of these indicator, class indicator variables. And the more entropy, the better the class variable is identified, the better the separation of the classes is. And so we change the thresholds and we get different entropy values, and we change also the sample size here. But in all the cases, the pseudo-class approach leads to substantial biases. The three-step procedure, almost no biases at all. This is the mean square there, the second column, and it's always much bigger for the pseudo-class methods. And finally, it's the coverage, and you can see it's it can get really bad here when you increase the sample size with the pseudo-class method. The pseudo-class method, it's nothing more than basically using the the most likely class membership variable as an observed variable. That's all it does, basically. And that's basically ignoring the measurement error in the most likely class variable, right? That's what it does. The difference between this method, the pseudo-class method, and the three-step procedure is not acknowledging that the most likely class variable has a measurement error in it. Anyway, you can see with the three-step procedure, you get a little bit of coverage problems when, in certain cases, when the entropy is low. But in principle, it's works fairly well. And the other thing you want to see here is also that the one-step procedure, the efficiency, looking at the mean squared error here, comparing the mean squared error between the three-step procedure and the one-step procedure, you see that it's almost the same. So in many cases, it is, well, when the entropy drops, then the efficiency actually, there is some efficiency loss. But as long as you have a fairly good class separation, the three-step procedure actually works extremely well. And also here's another simulation for the C on X regression, and the same thing, essentially you see the same thing here. Oh, by the way, the original article by Vermont was basically only on the C on X regression, but you know, we can't contain ourselves with Bengt, and we did it basically for everything now. So yeah, it's you can actually use. So we did it for distal outcomes automatically, and then after the break, I'm going to show you how you can do it for any kind of model. So we have these 5 types of auxiliary variables that we have now in Mplus, but basically you have the all these processes automated, right? The 3-step procedure is automated. All you need to say is auxiliary equal. And you specify the variable, and you're going to get whatever you want, either as a distal outcome, where a variable is regressed from the latent class variable, or you're going to get it as a predictor variable. And you can actually specify many variables. For example, in that genetic application, one of the problems is that, they have thousands of predictors. And of course, you put thousands of predictors to a model that has like 4 indicator variables or something like that, the degrees of freedom, it's incredible. This is going to, the covariates will dominate the model. And so you can specify many, many predictors here and not keep the latent class variable intact. The latent class variable is going to be defined only by the indicator variables. In any case, so let's just look again at this C on X regression. So again, the pseudo class gives quite poor values, biased estimates, mean squared error much bigger than the 3-step procedure. And look at the coverage here. It's quite incredible that the 3-step procedure does even on the C on X regression. And again, the loss of efficiency, even in the worst case with the entropy 0.5, is not that big actually. And as long as the entropy is good, 0.7, 0.6, yeah, there's no loss of efficiency at all. The mean squared error is the same between the 2 methods. So it works really, really well. And finally, I wanted to say, this work by Vermont was done kind of in the same time we were working on the same thing. So, the Mplus group. So we have actually exhaustive simulation in this paper that's on the website, which actually explores multiple other methods. So the most likely class membership regression, all kinds of probability-weighted regressions, even Bayes imputation. We actually tried, the Bayes imputation is not part of this article, but we basically tried Bayesian imputation for the latent class variables, and none of these methods actually work. And so you basically got really extensive simulations to show that all these methods actually lead to bias estimates, and this new 3-step procedure actually works pretty well. So with that, I think we'll just see if you guys have any questions, and otherwise we'll let you go for a while. Analysis. So you can actually have a latent, some kind of a growth mixture model or any kind of thing. So it works with no restrictions, basically. Yeah?
How does this method relate to the endogeneity problem, which is theoretical? The endogeneity problem is that some of the elements are affected by others at the same time. So I'm not sure how how this relates or answers.
Do you want to repeat that question?
Yes. My question is the following. The endogeneity problem is important is important in many situations. How does this relate?
I'm not sure what you mean by endogeneity problem.
I think you have to explain what the endogeneity
Right,
problem is to
yeah.
the audience.